Hello, Complex gang. Hope you guys are doing well on this Friday evening. I decided that I couldn't rest this weekend without finishing the course. So this is the last lecture series for complex analysis. Our goal today, we're going to end up doing a improper integral of a real function, but we need to look at a couple of tools along the way and then develop some techniques. So I need one more tool for computing residues. For whatever reason, I didn't look at this in the last lecture series. Probably should have been giving you some homework, but oh well. So this is a specific tool for computing the residues of a rational function of complex numbers. So we're going to be studying f of z is p of z over q of z. And I want to assume that both p of z and q of z are analytic at z naught. And I want to go ahead and assume three things. So p of z naught is not 0. Q of z naught is 0, and q prime, the derivative of q at z naught, is not 0. If those three things hold, then the rational function p over q has a simple pole at z naught, and the residue is really easy to compute. It's just p of z naught over q prime of z naught. And that's not a formula that we saw before, and we're going to want that just to be able to compute some residues a little bit easier. So let's do just a quick example of this before we go on to make sure that everything is crystal clear. So let's, that's not going to show up, is it? Let's do, I'm going to think about my p of z is going to be my z, and my q of z will be z squared plus 1. That's why I'm thinking about this. Then let's just going to think about the residue of f at I. You can see that f has a singularity at plus or minus I. These are actually isolated singularities. They're actually both simple poles. How do we see that? Let's just do one of them. So notice that p of I is not 0. P of I is not 0. Q of I is 0. But Q prime of I, Q prime is 2z. Q prime of I is 2i, which is not 0. And so immediately from our theorem, we know that f has a simple pole at I. And in fact, the residue at z equals I of f is just p of I over q prime of I, which is I over 2i, which is 1/2. So it's a really nice way to be able to compute residues in this case. So I wanted to look at just review some things with you. So first off, we talked about this way back at the beginning when Dr. Dixon was just getting us started. We've come a long way since then. You guys have done really well. We looked at just these two basic tools, and this is the triangle inequality. This is the reverse triangle inequality. This one I think we're all pretty familiar with, but I'm going to make use of this guy right here. So the modulus of z1 plus or minus z2 is always greater than or equal to the absolute value of the modulus of z1 minus the modulus of z2. These outside bars are absolute value because the inside is a real number. So I'm going to need that down the road with some of the things that we run into. I think I'll stop this video here. We need one more tool, and then we're going to dive in and learn how to use the theory of residues to actually compute some real valued integrals, some integrals of real valued functions.